Well, hello my dear students and viewers. In this lecture, we are going to start a new unit of the course, the Unit 5 on unconstrained optimization algorithms. So far, we have been describing first order, second order optimality conditions for a function of several variables. Now, in this lecture, we will consider an unconstrained optimization problem, that is minimization of a function of several variables, and a standing assumption on the given function, which we call as the objective function, is that the objective function is continuously differentiable. Now, given this set of this unconstrained optimization problem, now our task is how to find a minimizer, a minimum point of this function. Towards this, to find a minimizer, we aim to develop algorithms, mathematical procedure, mathematical methods to reach an optimum solution, a minimum point of the given objective function. Those we call optimization algorithms for unconstrained optimization problems. In this lecture, we are going to know general structure of unconstrained optimization algorithms. After knowing the general structure of unconstrained optimization algorithms, we will also learn a few terminologies. Those are related to the general structure. Those are the descent property, quadratic termination property, global convergence property, and the notion of line search for an unconstrained optimization algorithm. A general optimization algorithm to optimize a function of several variables, say the function f, depending on n many number of variables, which is known to be having continuous partial derivatives of first order, we commonly proceed as follows. That to find a local minimum of the function f, we start with an initial point, say x naught. Then at the point x naught, we find a descent direction of the function f. Let's suppose we choose a direction, say d naught, that is a descent direction of the function f at the point x naught. Identifying this descent direction d naught, we find a step length, let's suppose alpha naught, to be taken along the direction d naught. After taking this step length alpha naught along the direction d naught, we reach at the point, say x1. Reaching at x1, we identify a descent direction of the function f again. Let's suppose we choose this direction to be a descent direction of the function f. After identifying this descent direction d1, we take a step length to be taken along the direction d1, say an amount of length alpha 1. By taking this step length of alpha 1 along the direction of d1, we reach at the point x2, and reaching at the point x2, we again endeavor for identifying a descent direction and take a step length along this direction, find the next alternative point, and so on. In general, reaching at the point xk, we identify a descent direction of the function f at the point xk, then take a step length, reach at the point xk plus 1, and keep continuing this process until and unless we reach at a point at which a local minimum of the function f is realized, or unless and until we reach at a point at which a necessary condition to be local minimizer is realized. That means you keep continuing this entire process unless and until we reach at a point xk at which we have gradient of the function at the point xk is a null vector. As in numerical computation, identification of a point xk at which this exact equation is satisfied is rarely possible. What we do, we consider a precision, say epsilon greater than 0, and we endeavor identification of a point xk at which the norm of the function f at the point xk is less than epsilon. By that, we are getting approximately a point xk that satisfies almost this equation. Thus, in a general optimization algorithm, to find a local minimum of a function of several variables that is known to be having first order continuous partial derivatives, we start with providing an initial point x naught and pass a precision level epsilon that indicates a desired tolerance level for the equation grad f is equal to 0, which might give us an optimum solution or at least a stationary point. Then we set our counter, the iteration number 2b is equal to 0, and move to the main steps that you check whether the current iterate xk is a stationary point, which is checked by checking that norm of f xk is less than epsilon or not. If not less than epsilon, then we go for finding a descent direction at the point xk. After identifying a descent direction dk at xk, we go for computing a step length, say alpha k, along the direction dk at the point xk. After identifying a step length, we update the current iterate by xk plus 1, which is given by xk plus alpha k dk, and increase the iteration counter number by k plus 1, and next go for checking whether now the current iterate xk plus 1 is satisfying this stopping condition that norm of fxk is less than epsilon or not. So in the main steps, the beginning step, let us suppose call it as step 1 of the main step, we check for optimality or stationarity of the point xk. When the current iterate is not a stationary point, we repeat these following steps. We name those steps as, let's suppose, step 2, step 3, step 4, and step 5. While xk is not a stationary point, we repeat the step numbers 2 to 5, and when this norm of fxk is less than epsilon, we stop the algorithm providing xk as a possible local minimizer of the function f. So right here, otherwise we give the point xk as an output of the algorithm which is at least approximately a stationary point. So by this general algorithm, we notice that we are actually endeavoring identification of a sequence of iterates xk's that has the elements as x0, then x1, then x2, x3, and so on, which at the end of the day, by evaluation of the entire optimization algorithm, provides us a point xk for which this inequality is realized. If an optimization algorithm is able to generate a sequence xk which ends up identifying an optimum solution or a minimum point of the function f, then we call such an optimization algorithm globally convergent. If, however, when an optimization algorithm is not globally convergent, it may still generate a sequence that converges to a point satisfying the first order necessary optimality condition, provided the initial point x naught is sufficiently close to that point. In this case, we say that the algorithm is locally convergent. Let us write out these two definitions: global convergence and local convergence of an optimization algorithm. By global convergence, we mean that an optimization algorithm is said to be globally convergent if for any arbitrary starting point x node that is taken from the entire global region of the n-dimensional Euclidean space Rn, the algorithm is guaranteed to generate a sequence that converges to a point that satisfies the first order necessary optimality condition of optimality. The word global in global convergence is due to the fact that the initial point x naught can be chosen arbitrarily from the entire global or universal region Rn. By local convergence, we mean when this entire phenomenon is true, when x naught is chosen from a sufficiently close neighborhood of an optimum point of the function f. We write this local convergence as follows. When an optimization algorithm is not globally convergent, it may still generate a sequence that converges to a point satisfying the first order necessary optimality condition, provided the initial point is chosen from a sufficiently close neighborhood of the point, a point that satisfies first order necessary optimality condition. In such a case, we say that the algorithm is locally convergent. The term locally here is due to the fact that the algorithm is converging only when the initial point x naught is chosen from a local neighborhood of the point x bar that satisfies the first order necessary optimality condition that grad fx bar is equal to 0. Now we notice that in a general optimization algorithm, step 2 over here in these main steps, we take the direction dk as a descent direction, and therefore if we move from the point xk along the descent direction, then along the direction dk there exists at least a small amount of step length, say delta, for which we have the property that the function value at any point over here from the point xk to the point till having this delta distance, that is xk plus lambda dk, is less than that of at the point xk. We choose the step length in a step 3 so that this inequation is valid, and therefore in the next iterate at xk plus 1 the function value is certainly smaller than that of at the point xk. When the algorithm generates a sequence xk so that in the consecutive iterates the function values are degrading, that is fxk plus 1 is less than fxk, then we call such an optimization algorithm having the descent property. We write this descent property neatly over here that an optimization algorithm is said to have descent property if any sequence generated by the algorithm, say xk, satisfies f of xk plus 1 less than f of xk, when the point xk is not a stationary point. Now next I will discuss the notion of quadratic termination property. You know, while checking efficiency of an optimization algorithm, we commonly employ the optimization algorithm on a strictly convex quadratic function, because a Taylor's quadratic approximation of a function retains the first order and the second order derivative informations of the given objective function. And we all know the first order derivative information of a function f gives us the monotonic nature of the function, that it checks out whether at a given point the function f is monotonically increasing or decreasing. And the second order information we all know gives us a local curvature information or the bending information of the surface of the given function. And this monotonic nature and a local curvature information at a point xk of a given function of several variables commonly indicate whether the current iterate xk is close to an optimum solution. Because we all know at a given point x bar, if there is no ups and downs or monotonic nature of the function f, that is grad f x bar is equal to 0, and the Hessian of the function f at the point x bar that involves the second order partial derivative informations. If the Hessian is positive definite, then the point x bar is a local minimum. As the Taylor's quadratic approximation or any other quadratic approximation of a given function of several variables retains of the first order derivative information and the second order derivative information of the given function f, we check efficiency of an optimization algorithm by checking how efficient the optimization algorithm for a quadratic function. An optimization algorithm for functions of several variables, say of n variables, is said to have quadratic termination property if it terminates with an optimum solution or with the minimum point within at most n steps the number of variables of the function when applied to the minimization of strictly convex quadratic function. That is when the optimization algorithm is applied on a function having the expression of the type of x transpose qx plus some vector b transpose x plus some constant c, where q is a positive definite matrix. The algorithm generates a sequence with the initial point x0, next iterate as x1 till xn minus 1, so that within these n many points we have a point at which this grad qx is equal to 0. This equation is satisfied. Now let us go back to the general optimization algorithm once more, and we see that out of these 5 steps in the main steps, we got to know what for this condition is, we got to know what is a descent direction decay in one of the previous lectures. In next few lectures we will consider to discuss in detail how to find efficiently a descent direction in this step 2. Now here let me try to talk about the step 3, how to choose this step length alpha k. You notice that this alpha k acts as a step length to be taken along the direction dk. We choose alpha k such a manner that the function value at the next iterate xk plus 1 is smaller than at the previous iterate xk. Now when the direction dk is a descent direction, we notice that we have several points within this step length delta at which all the points are having the property that the function value at those points are all less than that of the point at xk. Therefore, which point out of all these points and accordingly which step length is to be chosen, that is a big question over here. As we are aiming for identification of a minimum point, what we commonly do is that you choose alpha k, so that alpha k gives the minimum most value of the function f along the direction dk emanated from the point xk. That means we take alpha k to be the argument of the minimum value of the function f along the line of dk emanated from the point xk. So we go for minimizing these function values fxk plus alpha dk over alpha greater than 0, and as here we are searching for a minimum point of the function f along a line, we commonly refer this identification of alpha k as a line search. We see that while identification this alpha k, we are actually identifying a minimizer of this function, which is a function of one variable along the line dk, and therefore optimization of one variable functions is commonly referred as a line search. Let me write out here this line search. We are under the question how to find the step length alpha k. This alpha k is the step to be taken at the point xk along the direction dk. Along the direction dk, the function f reduces to the function of the points lying in this ray. Any point in this ray can be presented by xk plus alpha dk, which is certainly a function of one variable. We denote it by phi alpha say. So in finding alpha k, we identify a point alpha that minimizes the function phi over alpha greater than 0. So alpha k is the argument point of the function phi at which the function phi gets a minimum value. This minimization or optimization of one variable functions is referred to as line search. Now here the question comes, how to find these alpha k values. As the function phi is a function of one variable, you may think that we will just go for solving the equation phi dash alpha is equal to 0 and figure out at what values of alphas this equation is satisfied, then filter out a point alpha at which this equation is satisfied, and the second derivative test phi double dash alpha greater than 0 is fulfilled. But here we notice that for a general expression for phi alpha, solution of this equation is not a trivial task, and moreover, we notice that this equation involves the derivative of the function phi. Computation of derivative value of a general function is not really a trivial task. So practically what we do is that instead of identifying an exact solution of this equation, or instead of considering an exact minimizer or a minimum point of the function phi, we consider an alpha k at which a sufficient decrease of the function value is attained, and as well the step length alpha k is not too small. That means instead of employing alpha k that exactly fulfill this requirement, we choose alpha k so that fulfills some acceptable conditions to realize the convergence of the optimization algorithm. Such an alpha k is called an acceptable or inexact step length. And when alpha k is chosen satisfying this, we call the alpha k an exact step length. So we name here that exact line search is the line search that searches for alpha k to be exactly a minimizer of the function f along the direction dk, and we refer inexact line searches as the case if we choose to employ an acceptable alpha k that satisfies a satisfactory descent property, that is the function value is sufficiently degraded in the next iterate, then Such a line search is called an approximate or acceptable or an inexact line search. So in an exact line search, if the function phi is differentiable, then accordingly the function phi is differentiable, and hence alpha k satisfies this equation. But for an inexact line search, the step alpha k does not necessarily satisfy this equation. Now, as I have mentioned earlier, you notice that this exact line search for a differentiable function commonly attempts to identify a solution of this equation. Commonly for a general given expression of the function f, the corresponding phi alpha is a nonlinear function, and therefore this equation is a nonlinear equation for a function of one variable. To identify a solution for this nonlinear equation, we can employ the root finding methods for a function of one variable. Apart from these root finding methods, we also can devise certain algorithms to identify a small interval of alpha values, say ak to bk, that includes a solution of this equation. An interval for the value of alpha that includes a minimizer of the function phi is called an interval of uncertainty. The term uncertainty is due to the fact that in the interval ak to bk, we are uncertain where the function phi is having a local minimum. As identification of an exact step length requires an iterative process to identify a solution of this equation, the optimization algorithms that employ exact line searches are computationally not efficient, because we notice that if we go for employing exact line search over this step 3, then inside this while loop for the main step, we are going to employ one more loop, one more iteration process to just resolve this step 3. And hence the computational cost required for the step 3 to be resolved gets multiplied with the computational cost that is required in the entire algorithm. Hence we commonly avoid exact line searches to be employed, and rather we go for an inexact line search where we just consider some alpha k to be chosen in the step 3 that satisfies just a mathematical condition, so that no loop or no iterative process is required to resolve the step 3. In the next lecture, I will discuss in detail 4 inexact line searches to identify step length in a step 3 of this general algorithm for optimization. As I will not go for discussing exact line search techniques to identify exact step length in the step 3, I will just mention a few commonly used methods for exact line search and also mention the references of those methods, so that if you are interested you can look at those methods for exact line searches. Before getting into mentioning exact line searches, let me tell you here is that in the general optimization algorithm, as we go for employing step length along the descent directions and hence getting the function values degraded from the point x0 to x1, then further degradation from the point x1 to x2 and so on, we call this general optimization algorithm also as general descent algorithm. Now let me mention commonly used exact line searches and their references. I will call here 3 special references. Those are the book by Bazara, Serali and Setti entitled Nonlinear Programming. Next, the book by Chong and Jack entitled An Introduction to Optimization, and the book by San and Wan entitled Optimization Theory and Methods. Exact line searches are categorized into 2 parts: the ones which uses derivative of the function phi and the ones which do not use derivatives. So for exact line searches, we have 2 categories. One is derivative free methods and another is the methods using derivatives. In derivative-free methods, we have two category of methods. Those are simultaneous search and another is sequential search. In simultaneous search, what we do is that to identify a minimum of the function phi over a given interval of uncertainty, say a to b, we divide the entire interval of uncertainties into n many points and then evaluate the function values at all these endpoints or grid points. Accordingly, we reduce the entire interval of uncertainty of length b minus a to some smaller length than that of b minus a. Next, again we divide this reduced interval of uncertainty into n many points. Further, we reduce the interval of uncertainty into smaller length. In this way, we reduce the interval of uncertainties into smaller and smaller length, where in the reduced intervals, the function phi is having a minimum. And finally, we reach at a very small interval of uncertainty from which we pick up a point and consider it to be a minimizer of the function phi. For the method in simultaneous search, you may please visit the book by Bazara, Serali and Sethi. In the sequential search, what we do is for a given interval of uncertainty, say A to B, we pick up 2 points, say lambda and mu. Then we evaluate the function values at lambda and mu. With the help of the values of the function phi at lambda and mu, we reduce the interval of uncertainty from AB to A2 mu or to lambda to B, so that in the reduced interval of uncertainty, the function is having a local minimum. So as if we are taking out two sections of the interval A to B and checking which section includes a minimum of the function phi, you go for reducing your entire interval of uncertainty from AB to that section which includes a minimum and discard the other section, and further in the reduced interval you now again take two sections of this interval A to mu, iteratively go for picking up that section out of the two sections of the interval of uncertainty which includes a minimum. In this way, you reduce the interval of uncertainty of the function phi. Finally, get a very small interval of uncertainty that includes a minimum of the function phi. And you pick up any point from that small interval of uncertainty as an exact step length to be employed in the optimization algorithm. So the sequential searches are usually also referred as section methods. Common section methods that are popular in optimization algorithms are dichotomous search, the golden section method, and the Fibonacci section method. For the dichotomous search, you may please visit the book by Bazara, Serali and Sethi. And for a fabulous discussion on golden section method and Fibonacci section method and their interrelationship, you please visit the book by Chong and Jack. The discussion given in Chong and Jack's book on golden section and Fibonacci section method is so attractive that the section interrelating Fibonacci section and golden section method pulls me to read and flip all the pages of the Chong's and Jack's book. And Chong and Jack's book is the only one book that I have read so far that interrelates between golden section and Fibonacci section method. I strongly suggest you to read this section, golden section and Fibonacci section method from Chong and Jack's book. Now, using derivatives, the methods for exact line searches are categorized into two parts. Those are section method, which are similar to sectioning of the interval of uncertainty like this sequential search. But here in this section method, we not only use the function value but also the derivative value of the function to reduce the interval of uncertainties. For a reference of these section methods for using derivatives, you may please visit the book of Bazarasarali and Setti. The other category of exact line search method for using derivatives is the approximation methods, and commonly used approximation methods are the root finding methods for functions of one variable. Those are Newton method, which can be found from Bajra and Setti's book. Next, the second method, a root finding method for a function of one variable, which can also be found from the book by Chong and Jack. Another method is interpolation methods. For a detailed discussion on interpolation methods for exact line search, a nice reference is the Sun and One's book. With these all references and categorization of exact line search methods, I end up this lecture here. In the next lecture, we shall consider discussion on inexact line search, where we will detail four particular inexact line search methods. Those are Armijo backtracking, Armijo-Goldstein rule, Wolff-Powell rule, and the strong Wolff-Powell rule. Now I extend my heartfelt thanks for listening this lecture. Thank you. Thank you all.